Thanks, Laura, for the invitation and the introduction. So it's very nice to participate at this meeting, although hopefully next time it will be in person. I really hope so. So I want to talk about Galois representations attached to hyperelliptic curves. And in the first few minutes of this talk, I'm going to be quite general. But quite soon I'm going to specialize to some cases of interest that I have been studying during my PhD. So for now, let's take any field K. For simplicity, let's take it of characteristic different from 2. It's not strictly necessary, but when I will specialize, I will have fields of characteristic 0. So this is really not a problem. And I am going to identify a hyperelliptic curve x over k with some curve with its defining equation. So actually, this is the equation defining the function field. And this will be given by a polynomial in 2 variables of the form y² equal f of x, where f is a polynomial of degree at least 3, which is separable. And I will denote the curve by x throughout the talk. And the genus of x, g, will be related with the defining equation by the fact that the degree of f is either 2g plus 1 or 2g plus 2. I'm not explicitly excluding the case where g is equal to 1. So normally elliptic curves are not hyperelliptic, but actually the results that I will eventually present will be also true for elliptic curves. So I will just implicitly include them in my definition. First big ugly difference between higher genus curves and hyperelliptic curves is that a hyperelliptic curve will not be an abelian variety, but we would like to find similarities between hyperelliptic and elliptic curves. So instead of studying directly x, we will study its associated Jacobian variety, which I will denote by J. And this abelian variety will have dimension G, and will coincide with up to isomorphism with the curve I was beginning with, exactly when my curve was an elliptic curve. But this is very useful objects to look at, since the set of the points on the Jacobian which are defined over k bar, where k bar is some separable algebraic closure of k, happens to be an abelian group. And in particular, I will look at points of finite order on this group. So this is very standard definition, but just to fix the notation once and for all, let me say that the subset, which is actually a subgroup of m torsion points, will be denoted by J of m for any m an integer. And these are the points in J k bar, which have order dividing m. And I will also want to pack up as much information as possible coming from m torsion points. And in order to do so, I will define the L dictate module of J for any prime L by taking the inverse limit of torsion of order a power of L. Normally I'm going to study these more complicated objects here. And I aim in the next few minutes at defining a Galois representation, which is given by some action on this object here. So as already said, J of m is a subgroup of J of k, and the Tate module is a module over the ring of integers CL. I can say something more. Indeed, I will just state the result in the case of a characteristic not dividing M or L, although there are more general results also in these two cases, only I'm not going to need them today. It is well known that the M torsion has as the group structure of the direct product of 2G copies of the cyclic group of order M. And by taking the inverse limit, one proves that the Tate module is free of rank 2G over ZL. Okay, so I'm going to study these objects, and it's now time to define a Galois action on them. So there are several ways to do that, but I like things to be as explicit as possible. So I will give a very down-to-earth definition for this Galois action. So first of all, let's fix the Galois group that we want to act on our objects. So remember, K was our field of definition for the curve and hence the Jacobian. And we denote by GK its absolute Galois group. Then it will act on the points of J with coordinates in which are defined over K bar. And this action can be simply defined by acting coordinate-wise. So the coordinates will be some elements in K bar, and they will satisfy some equations over K. And if we transform these coordinates by elements of GK, we will still obtain a point that satisfies the same set of equations, so a point on J. And this action happens to be linear. So in particular, it restricts to torsion, and it will induce two representations, one of JM, two sets of representations, one on JM for every M, and one by, again, taking the inverse limit on the Tate module. And these isomorphisms here that give the group and module structure also agree with this Galois action. Therefore, we are ready to define the representations that we want to work with. We have the representation defined by the action on M torsion, which is denoted by rho M bar. It's called the mod M Galois representation. And the one on the L-adic Tate module, denoted by rho L without the bar, is called the L-adic Galois representation. And this is the representation that I will study. Indeed, this object encodes information also on the representations mod M, because we have that if we take the representation, the L-adic representation, and reduce it modulo L to the N for any N, we recover the mod L to the N Galois representation, which makes the notation and the terminology sensible. Also, I will slightly abuse the notation by also calling rho L the same representation, but seen as with image in this larger group. And this will be after choosing a basis isomorphic to GL2G of QL bar. And I will do that because I prefer representation theory on vector spaces over algebraically closed fields rather than modules over rings that are much, much smaller. And this will make determining these representations a bit easier. So at this point, we are going to face some very difficult problems, and we need to find a direction to go. Indeed, one would be normally interested in studying maybe the arithmetic properties of a hyperelliptic curve defined over the rational fields, or the number field, some number field, because it can be relevant for the Diophantine problems. And in particular, if the arithmetic properties we're interested in are the Galois representation, the first obstacle is to determine as much information as possible on the Galois group, the absolute Galois group of this number field while the curve is fine. And these problems are already very, very difficult to tackle. So what I will do instead is to work locally, and more precisely, we have this simple but important remark that our very complicated Galois group of number field contains, as the composition groups, copies of the absolute Galois group of local fields. namely all the completions at the various primes. And so if we study separately all the Galois representation attached to the curves seen over the local completions, we can hope to find information about the general Galois representation. So I will focus on this sub-problem now. And moreover, the Galois representation of a curve over a p-adic field is related to the geometry of the curve, and in particular to the reduction of the curve. And this is quite interesting, and I will come back to that in a few minutes. So are there any questions so far? All is good, I'll go on. So as I said, the Galois group of a p-adic field is easier to handle. So from this moment on, I will just fix K to be a p-adic field, so some finite extension of QP. I will also take P to be odd, because the results that I will end up presenting will make sense for P odd. And I will denote by lower case K its residue field, which will be some finite field of characteristic equal to P. Okay, so what does the Galois group of K, the absolute Galois group of K look like? Well, it sits inside some very nice short exact sequence where the element here on the left is the inertia subgroup, which is given by precisely those elements in the Galois group that acts trivially on the residue field. And here we have the absolute Galois group of the residue field, which is quite nice to study. And before I say something more about that, let me remind you that these two groups can be realized as Galois groups of certain intermediate extensions between K and K bar. Namely, if we take the maximal and ramified extension of K, then we have that the inertia group is isomorphic to the Galois group of K bar over K unramified. And well, the quotient is, of course, what you expect it to be. So the Galois group of K unramified over K, which we know to be isomorphic to the absolute Galois group of the residue field. Now, the inertia subgroup is quite complicated. It will contain a wild subgroup, which will mess things up, but also make things interesting. And actually, at some point, we will focus precisely on this wild subgroup. And the tame part, which is much more well-behaved, and that's the reason why most of the results in the literature, also in the quite recent literature, focus on the tame K, on the tame inertia action. But the Galois group of lowercase k is much simpler. Indeed, it is procyclic, and its generator is the Frobenius, which on lowercase k bar acts by raising elements to the power of size of k, size of the residue field. So I'm going to need to take some Frobenius elements in the group G capital K. And for now, I will just fix any lift of this Frobenius element in GK, in G capital K. And I will still call it Frobenius, denoted by this Frob K. In some cases, this choice will not be particularly relevant as far as the Galois action is concerned. In other cases, it will be, and I will make clear what happens when. So ideally, if we are capable of studying the inertia, the restriction to inertia and the action of Frobenius, and see also how these two things talk to each other, we will determine completely the Galois representation of a curve defined over p-adic field. So let's now see how, vaguely speaking, these Galois representations are related to the geometry of the curve, as I was starting to say earlier. So let's take our elliptic curve x over k, and we will denote by x sub smaller k its reduction, that is changed to CD field. We can construct a model for this reduction by taking a suitable equation for x and taking all the coefficients reduced modulo the maximal ideal of k. And this will describe the equation of the curve x sub k. The problem is that this curve will be in general not smooth anymore. And remember, one of the conditions, the geometric conditions for the curve to be hyperelliptic was that the curve was smooth. And we say that x over k has good reduction precisely when this happens. We say that it has potentially good reduction if this happens after base changing to some finite extension f over k. And otherwise, we say that the curve has geometrically bad reduction. Now, geometrical bad reduction types can be a lot as soon as the genus is high. And I didn't give precise definitions for these because the cases I will focus on today are the first two, and in particular, the potentially good reduction case. Observe that if X has good reduction or also potentially good reduction, the same holds true for the Jacobian variety, and the converse will not be true. Because of this reason, I will be able to use some tools that come from properties of abelian varieties, and will apply them in the setting of curves which have potentially good reduction. Although this is not really necessary for proving the results that I will present, but it will be useful if one just wants to work with curves and not care too much about the associated Jacobian varieties, which may be some horrible objects to look at. So the first tool that I will use is the criterion of Neronov-Shafarevich that pins down the exact cases where the Jacobian variety has good reduction and tells us what happens to the Galois representation, the Alladic Galois representation. So actually this criterion has a statement that is longer and more precise, but I'm just going to use this equivalence. So let's fix a prime L different from P. And note that it will not be important which prime we fix as long as it's not P, and everything will be the same. And we have that J over K has good reduction if and only if the restriction to inertia of the Alladic Galois representation is trivial. So to be more precise, it is equivalent that there exists a prime L different from P for which this representation is trivial, and that for any prime L different from P, this also holds. And of course, the condition on the left is independent on L. Which suggests that the condition on the right also has to. So this makes representations of curves or more in general Jacobian varieties with good reduction quite easy to study, because if the restriction to inertia is trivial, we just need to find out what is the image of Frobenius, and then we know everything about the representation. And the study of the image of Frobenius can be reduced to a problem of point counting, since the characteristic polynomial of the Frobenius, first of all, it will not depend on the choice of Frobenius we make, precisely because the restriction to inertia is trivial and the Frobenius will be defined up to inertia. This polynomial here is related to the zeta function of the reduced curve. So up to taking some sign correctly, it's exactly the L factor of the zeta function. And to compute that, we just need to compute to count points on the reduced curve, which is not too difficult to do. So good reduction case is pretty much well understood, but an important corollary of this criterion allows us to also determine the case, to determine what are the case of potentially good reduction of the Jacobian variety. Indeed, they will correspond precisely to the case where the image of inertia is finite. So the restriction to inertia will factor through some finite quotient. And we will want to do that. So now, what is known? Well, for the case of elliptic curves, everything is known. So I summarized in this table what are the tools needed for the various cases, but in the interest of time, I will not spend more time on that. I just want to make you notice that the sort of longer case in this table is potentially good reduction case, where one needs to distinguish between I wrote tame and wild, by which I mean that the minimal extension where the curve acquires potentially good reduction is respectively tamely or wildly ramified. And this tame case was studied first. And the same approach that has been employed for it turns out to be ineffective in the study of the wild case. But a representation theoretic approach worked in the wild case, and this ideas will be also used in the results that I'm going to present about hyperelliptic curves with wild reduction. In the genus, in the higher genus case, most of the known results are on the tame case, and there are some partial results on the wild cases. So let's see immediately one of them. So as I also wrote in the abstract, these are like the vague hypotheses that I want to assume before stating my main result. And I will spend a couple of minutes making them a bit clearer. So I want to take a curve of genus G with potentially good reduction, which implies also the Jacobian has potentially good reduction. And so K will be some extension of QP. And I want P to be the largest wild prime. And I want the good reduction to be attained over an extension which is as large as possible. So what do these two things really mean? So let's start with the largest wild prime thing. So by a result of Serentate, we know that if P is larger than 2G plus 1, then automatically both the curve and the Jacobian will have tame reduction. So if we want to hope to have a wild prime, we need to look at smallest primes. For example, in the elliptic curves case, only 2 and 3 can be wild primes. So I will make this hypothesis. I will assume that 2G plus 1 is a prime. And I will furthermore take a model for my curve, which is given by an equation of this form, where the defining polynomial has precisely degree P. So we knew it could have degree either 2G plus 1 or 2G plus 2. We will take an odd model. And we want this odd degree to be actually my bad prime, my prime at which we consider the reduction. And this will be the first hypothesis I make. And now moving on to the large extension. Well, this will be related to the image of inertia under the Galois representation, which we know is finite. But actually, again, Serentate tell us how to determine this extension here. Indeed, we have that our image of inertia is isomorphic to the Galois group of this extension, where K unramified of Jm is the minimal field extension, where M torsion points are defined. So it's some Galois extension. And this holds for any integer m that is at least 3 and not divisible by p, which is quite impressive because it also means that this Galois group here is independent on the choice of m. And by Neronov-Sheferevich, we have that this extension here will actually be the minimal extension where my Jacobian and actually also my curve acquires good reduction. So at this point, let's take M, for which we know how to compute this field here. For example, when M is equal to 4, a theorem of Yelton tells us how explicitly to determine this field. And at this point, I'm ready to make assumptions on this field extension to be large. First of all, I want its degree to be divisible by P, otherwise we are not in the wild case, so it's not interesting. And second, I can prove using this description that this field here is always a subgroup of a certain explicitly given semi-direct product of the group of, or the cyclic group of order P and the cyclic group of order 2 times P minus 1. It's not really important for today what semi-direct product is, as long as you trust me that it can be described. And so the third and final hypothesis that I make is that we don't only have a containment, but actually an isomorphism. So you may wonder if this makes sense, if there are any curves at all with this property. So let me give a couple of examples. First of all, these very simple looking curves are all examples. So y squared equal to x to the p plus p, or also minus p over qp, all work. And also more in general, if you take y squared equal a polynomial in x, which is reducible over k, and with this condition on the valuation of the discriminant, we also obtain a curve over k, which satisfies the hypothesis h1, h2, h3. So we are not doing an empty theory. We can actually apply my result. And for all these curves, we have, first of all, that there exists a finite extension that I can compute explicitly, which is totally ramified of degree equal to the size of the inertia image, such that we can base change our original curve and compute its reduction. And we will always find this model here of the residue field, which is quite impressive because it doesn't depend on the curve. To be fair, the field F does depend on the curve, but the fact that it is so large ensures that you can always find this very simple looking model for the reduction. And now, well, I need to fix my Frobenius at this point because it will not be, it will only be defined up to inertia, so I will need to make a choice. And I will take it to be the Frobenius element that fixes this field. And I also need to fix some element of order P. And I will take this one where the alpha i's, I didn't go into too much details, but they were the roots of the defining polynomial f. And it's not really important. The important thing is that I need to fix some element of order P in the inertia subgroup. And now the main theorem is that if my hypothesis H1, H2, and H3 hold, then I can write my rho L as the tensor product of two much simpler representations, chi and psi, where chi is a character, it is unramified, and it sends the Frobenius element that I just fixed to a certain number, which is determined essentially by looking at point counting again. And psi is a representation of dimension 2G of a finite group, which is this group here. It's almost the same as the one giving the image of inertia, but this is an extension over K. And it is actually the Galois closure of my F over K, where F is the one given by the previous lemma. And this psi is completely determined by three properties. So it's irreducible and faithful. And this is actually enough in the case where K over QP has even inertia degree. And I need an extra condition if this inertia degree is odd. And this is what's the trace of the product of these two elements that I had to pick before the statement of the theorem. So the point is that in the case of, in the second case of odd inertia degree, this field extension here this Galois group here has two irreducible and faithful representations, and they can be distinguished exactly by looking at the trace of the elements of the form sigma times Frobenius, where sigma is a wild element of order P. And they only differ by a sign. They are always of this form, but there's either a plus or a minus in front of them. And this thing here, this statement here that this representation is completely determined by these three properties is completely representation theoretic. So you just look at the group, the representation of finite groups of the form that you obtain by explicitly computing this group here. And finally, the computation of the trace is done again via point counting. And I also have, to be fair, an example which is done via computation in Magma, but maybe I'm over time, so.
If you want to have 1-2 minutes, you can have it. It depends on how much you.
Well, it's already prepared. So I took the prime P to be equal to 5. So we have a curve of genus 2 over Q5. And this is one of the first examples that I wrote. So the curve equal to y squared equal x cubed plus 5. And my function here computes the Galois representation, taking as an input just this defining polynomial. And in a few seconds, it spits out what the representation is. So it has dimension 4 as we expect. And it's the product of this unramified character. And the rest is my psi. And it is given in terms of the string that corresponds to the character of this representation, seen as a representation of this group G, which is the Galois group of fourth torsion. And as bonus, this code also spits out the image of inertia and the conductor of the representation, which is always useful to know. And yeah, now I'm really finished.
Okay.